In the darkness of space, billions of galaxies float like islands in an infinite ocean. Each contains hundreds of billions of stars. Each star might harbor planets. And yet, from the greatest distance we can observe, these galaxies are not scattered randomly. They form patterns, vast cosmic webs stretching across hundreds of millions of light years, sheets and filaments of light separated by enormous voids where almost nothing exists. This is the shape of the universe. It is a shape that should not exist. In the beginning, moments after the Big Bang, the universe was nearly perfectly smooth, almost uniform in every direction. The temperature varied by less than 1 part in 100,000 from place to place. How did such smoothness become such structure? How did tiny ripples become the cosmic architecture we see today? This is a detective story spanning 13.8 billion years. It is a journey from the first fraction of a second after creation to the vast web of galaxies we observe today. Along the way, we will witness the universe's first moments, meet the invisible scaffolding that shapes everything we see, and discover that most of the universe is made of something we cannot touch, cannot see, and do not yet fully understand. The universe has a shape. Let us discover how it got that way. Look up on a clear night, far from city lights. The darkness between the stars seems empty, void, nothing. But it is not empty. It is filled with light so ancient that it has traveled for 13.8 billion years to reach your eyes. This light is stretched and cooled by cosmic expansion until it exists not as visible light but as microwaves, invisible to human eyes but detectable by specialized instruments. This is the cosmic microwave background, the afterglow of the Big Bang itself, the oldest light in the universe. When we map this radiation across the entire sky, we see something remarkable. The universe, as it existed 380,000 years after its birth, was almost perfectly uniform. Almost. Tiny fluctuations, temperature variations revealing density differences ripple across the ancient sky. These ripples are the seeds of everything that would come later. Every galaxy, every star, every planet, every person owes their existence to these tiny primordial variations. These fluctuations have a characteristic pattern, a statistical signature encoded in what cosmologists call the angular power spectrum. Imagine measuring the temperature difference between 2 points on the sky, separated by various angles. For very small angles, the differences are small. For certain intermediate angles, around 1 degree, the differences reach a maximum. For larger angles, the pattern shows additional peaks at predictable scales. This pattern is not random, but reflects physical processes in the early universe. The peaks correspond to acoustic oscillations, sound waves traveling through the primordial plasma before recombination. Regions of higher density compressed, creating pressure waves that propagated outward at a significant fraction of light speed. These waves created alternating regions of compression and rarefaction, hot and cold, visible today as the pattern of fluctuations in the CMB. The existence and precise location of these acoustic peaks confirms our models of the early universe with remarkable precision. The first peak tells us about the universe's curvature. The ratio between peaks reveals the balance between ordinary matter and dark matter. The overall amplitude constrains the primordial fluctuation strength. From these patterns, we extract fundamental cosmic parameters. But where did these density fluctuations originate? The answer lies in the universe's first moments, times so early that our understanding becomes uncertain, when the cosmos was compressed to densities we cannot recreate in any laboratory, when temperatures exceeded anything we can directly test. This is the frontier where physics meets philosophy, where observation meets speculation. Imagine the universe 1/1,000,000,000 of a trillionth of a trillionth of a second after the Big Bang. The entire observable cosmos, everything we can see with our most powerful telescopes, is compressed into a region smaller than a single atom. The temperature is 10 billion trillion degrees. Matter, as we know, it cannot exist. Even protons and neutrons have not yet formed. The universe is a seething soup of quarks, gluons, and energy in forms we can barely imagine. Then something extraordinary happens. The universe inflates. In a span of time so brief, it defies comprehension, perhaps lasting only until the universe is 100th of a trillionth of a trillionth of a trillionth of a second old. Space itself expands exponentially. The universe doubles in size, then doubles again and again and again, at least 60 times and possibly many more. In this moment, shorter than any conceivable measurement, a region smaller than an atom expands to become larger than our entire observable universe today. This is cosmic inflation, and it explains mysteries that otherwise have no explanation. To understand why inflation is necessary, consider a puzzle that plagued cosmologists for decades. When we look at the cosmic microwave background, we see a universe with remarkably uniform temperature in all directions. The temperature varies by less than 1 part in 100,000, no matter where we look. This uniformity seems natural until you realize what it implies. The observable universe extends roughly 46 billion light-years in all directions, a sphere 92 billion light-years across. Light from opposite edges of this sphere has been traveling toward us since shortly after the Big Bang, roughly 13.8 billion years. But these opposite edges are separated by 92 billion light-years. Even traveling at light speed, information could not have crossed this distance in the time available. These regions have never been in causal contact. They have never exchanged light or heat or any form of information. So how do they know to have the same temperature? This is called the horizon problem. Without inflation, there is no good answer. Regions that could never communicate somehow coordinated to have identical properties. It is as if you traveled to opposite sides of Earth and found everyone speaking the same language, wearing the same clothes, following the same customs, despite never having had contact with each other. Inflation solves this elegantly. Before inflation, the entire observable universe was compressed into a tiny region much smaller than an atom, a region where all parts were in thermal contact. This tiny region reached thermal equilibrium, settling to a uniform temperature through normal heat exchange. Then inflation occurred, exponentially stretching this small equilibrated region to become vastly larger than our current observable universe. What we observe today as causally disconnected regions were once close neighbors. They have the same temperature because they were once in contact, able to exchange energy and reach equilibrium. Inflation preserved this uniformity, even as it stretched space to cosmic scales. But inflation solves another puzzle too, the flatness problem. Space can be curved like the surface of a sphere or saddle. The amount of curvature depends on the universe's energy density. Too much energy creates positive curvature, a closed universe that would eventually recollapse. Too little creates negative curvature, an open universe that expands forever. The boundary between these, called flat or Euclidean space, requires a very specific energy density. Observations indicate our universe is remarkably flat, within measurement precision. The energy density is extremely close to this critical value, but flatness is unstable. As the universe expands, any deviation from perfect flatness grows rapidly. If the early universe were even slightly curved, by the present day it would be dramatically curved, obviously spherical or hyperbolic. Yet it is not. It is flat to extraordinary precision. This seems to require incredibly fine-tuned initial conditions, the energy density set to exactly the right value to an absurd number of decimal places. Why would the universe start with such special properties? Inflation explains this too. Inflation stretches space so dramatically that any initial curvature is flattened. Imagine drawing a circle on a balloon and then inflating the balloon to the size of Earth. The circle's curvature becomes imperceptible, appearing flat to anyone standing on it. Similarly, inflation stretches the universe so much that any initial curvature becomes undetectable. The universe appears flat, not because it started with special properties, but because inflation flattened whatever curvature existed. But what caused inflation? What drove this exponential expansion? The leading theory invokes a hypothetical scalar field called the inflaton, a quantum field permeating all of space. In its high-energy state, the inflaton field has unusual properties. Its energy density acts like dark energy, driving exponential expansion. As inflation proceeded, the inflaton field slowly rolled down its energy potential, like a ball rolling down a hill. When it reached the bottom, inflation ended. The energy stored in the inflaton field converted to ordinary matter and radiation, reheating the universe and beginning the hot Big Bang phase we trace through cosmic history. Without inflation, we cannot understand why the universe appears so uniform in all directions. Light from opposite sides of the observable universe, separated by nearly 90 billion light-years today, has identical properties, identical temperatures, identical characteristics. These regions have never been in contact with each other since the Big Bang. How do they know to be the same? Inflation answers this. Before inflation, all these distant regions were once close together in thermal contact, reaching equilibrium. Inflation then stretched this small equilibrated region to cosmic scales. But inflation does more than explain uniformity. It creates the seeds of structure. During inflation, quantum mechanics operates on cosmic scales. At the smallest scales, at the level of individual particles, the universe is never perfectly smooth. Quantum uncertainty. Heisenberg's principle ensures that energy fluctuates from moment to moment, from place to place. These quantum fluctuations are normally microscopic, confined to atomic scales, completely irrelevant to the large-scale structure of space. But during inflation, as space expands exponentially, these quantum fluctuations are stretched to enormous sizes. A fluctuation that begins smaller than a proton ends up larger than a galaxy, frozen into the fabric of space itself. These stretched quantum fluctuations become variations in the density of energy and matter. Some regions are slightly denser than average, others are slightly less dense. The differences are tiny, only 1 part in 100,000, but they are enough. As inflation ends and the universe transitions to normal expansion, these density variations survive. They are the ripples we see in the cosmic microwave background. They are the seeds from which all structure will grow. After inflation, the universe continues expanding and cooling, but now at a more leisurely pace. The exponential stretching has ended. Now we enter the radiation-dominated era, when the universe is so hot and dense that photons, particles of light, carry most of the energy. Within microseconds after inflation ends, quarks combine to form protons and neutrons. Within minutes, some of these protons and neutrons fuse to form the lightest elements: hydrogen, helium, a trace of lithium. But most of the universe remains hydrogen, single protons paired with single electrons. This is all the complex chemistry available. No carbon, no oxygen, no iron, no elements needed for planets or life. Those will come later, forged in the cores of stars not yet born. For 380,000 years, the universe remains opaque. Photons cannot travel far before scattering off free electrons. It is like trying to see through fog. Light exists, intense light filling the universe, but it cannot travel freely. The cosmos glows white-hot, then orange, then red as it cools, but remains opaque. Then comes recombination. Despite the name, it is actually the first time, not a recombination. As the universe cools below about 3,000 degrees, electrons and protons combine to form neutral hydrogen atoms. With electrons no longer free, photons suddenly find themselves able to travel without scattering. The fog clears, the universe becomes transparent. The photons released at this moment will travel through space for over 13 billion years, cooling and stretching as the universe expands, until some reach Earth where we detect them as the cosmic microwave background. They carry with them a snapshot of the universe as it was, a baby picture showing the tiny density variations that will shape everything to come. But now the universe enters the dark ages. With recombination complete, the brilliant glow of the early universe fades. Stars have not yet formed. Galaxies do not exist. The universe is dark, filled only with neutral hydrogen and helium gas cooling slowly in the blackness of space. This darkness will last for perhaps 100 million years, an eternity on human scales, but a brief moment in cosmic history. Yet in this darkness, structure is already forming. Gravity is at work. There is a problem. The density variations created during inflation and visible in the cosmic microwave background are tiny, only 1 part in 100,000. For ordinary matter, gravity acting on such small density differences would take far longer than the age of the universe to create the structures we observe. Galaxies should not exist yet. The universe should still be nearly uniform, with only slight clumping. But we see galaxies everywhere, fully formed systems containing billions of stars, existing when the universe was only a few billion years old. Something is missing from the story. That something is dark matter. We do not know what dark matter is made of. It does not emit light. It does not absorb light. It does not interact electromagnetically in any way we can detect. We know it exists only through its gravitational effects, the way it bends space and pulls on ordinary matter. But it is not optional, not a minor correction. Dark matter outweighs ordinary matter 5 to 1. For every kilogram of protons, neutrons, and electrons in the universe, there are 5 kilograms of something else, something dark, something mysterious. Dark matter has one crucial property that ordinary matter lacks. It does not interact with light. During the radiation-dominated era, when ordinary matter remains coupled to photons through electromagnetic forces, dark matter is free. Photon pressure cannot push dark matter around. Dark matter can collapse under gravity, while ordinary matter cannot. This changes everything. While ordinary matter remains nearly uniform, held smooth by photon pressure, dark matter begins collapsing immediately after inflation ends. The tiny density variations created during inflation serve as seeds. Regions slightly denser than average attract more dark matter through gravity. As dark matter accumulates, its gravity strengthens, pulling in even more dark matter. The rich get richer. Overdense regions grow denser, while underdense regions grow emptier. By the time of recombination, when ordinary matter finally decouples from light and becomes free to move, dark matter has already built a cosmic scaffolding. Dark matter halos, gravitational potential wells containing thousands, millions, eventually billions of solar masses, dot the universe. These halos are invisible. They emit no light. But their gravity is very real. When ordinary matter decouples from radiation, it finds itself in a universe already shaped by dark matter. Gas flows along gravitational gradients pulled into the potential wells created by dark matter halos. It is like water flowing downhill. The dark matter creates valleys, and ordinary matter fills them. This is how the universe gets its structure so quickly. Dark matter, immune to photon pressure, gets a head start of 380,000 years. By the time ordinary matter can respond to gravity, dark matter has already laid the foundations. The evidence for dark matter extends far beyond structure formation timing. Galaxy rotation curves provide some of the most compelling proof. When astronomers measure how fast stars orbit in galaxies at different distances from the center, they find something unexpected. In the outer regions, far from most visible matter, stars orbit much faster than gravity from visible matter alone could explain. They should fly off into space, yet they remain bound. Something invisible holds them in place. That something is dark matter. Extended halos of dark matter surround galaxies, providing additional gravity that keeps outer stars bound. The rotation curves can be explained precisely if dark matter outweighs visible matter by factors of 5 to 10 in these outer regions. Gravitational lensing provides another independent confirmation. When light from distant galaxies passes near massive galaxy clusters, the light bends, creating distorted images. By measuring these distortions, astronomers map the mass distribution. The results consistently show that most mass lies not where galaxies are brightest, but in extended diffuse halos, exactly matching dark matter predictions. Perhaps most dramatically, the bullet cluster shows dark matter and ordinary matter separating during a collision. Two galaxy clusters pass through each other at high speed. The galaxies passed through unscathed, but the hot gas between galaxies collided and remained at the collision site. Gravitational lensing reveals that most mass traveled with the galaxies, not the gas. Dark matter passed straight through, unaffected by electromagnetic forces that slowed the gas. This observation is difficult to explain without dark matter. Slowly, over millions of years, hydrogen and helium gas flows into the dark matter halos. As gas accumulates, it begins to collapse under its own gravity. But something opposes this collapse. As gas compresses, it heats up. Higher temperatures create higher pressures. Eventually, pressure balances gravity and collapse halts. For the gas to collapse further, it must cool, radiating away its thermal energy. Cooling is a problem in the early universe. Hydrogen and helium are inefficient coolants. They can radiate energy, but only slowly, only under specific conditions. The gas can become warm, tens of thousands of degrees, but struggles to cool further. Hydrogen atoms can radiate energy through specific quantum transitions. An electron in an excited energy level can drop to a lower level, emitting a photon carrying away the energy difference. But in the early universe, conditions make this difficult. The gas density is low, so collisions between atoms are rare. Without collisions to excite atoms, there are few photons emitted, little cooling. Molecular hydrogen, H2, is more effective. The molecule has rotational and vibrational energy levels in addition to electronic levels, providing more pathways for energy radiation. Molecular hydrogen can cool gas to temperatures around 1000 degrees Kelvin, much colder than atomic hydrogen allows. But forming molecular hydrogen requires special conditions and catalysts, making it relatively rare in the primordial gas. Nevertheless, in the densest regions, in the deepest dark matter potential wells, gas eventually cools enough to fragment into smaller clumps. These clumps continue contracting. At their centers, densities and temperatures rise steadily. Pressure increases as atoms pack closer together. The gas becomes opaque as photons scatter off the increasingly dense material. After perhaps 100 million years of darkness, at the center of the densest clumps, conditions finally become extreme enough for nuclear fusion. Hydrogen nuclei, single protons, collide with enough energy to overcome electromagnetic repulsion. They fuse, creating helium and releasing energy. The first stars are born. These first stars are unlike any we see today. They form from pure primordial hydrogen and helium with no heavier elements, no metals in the astronomer's vocabulary. Without metals to facilitate cooling, the first stars are probably very massive, perhaps 100 to 300 times the Sun's mass, possibly more. They burn incredibly hot and bright, with surfaces exceeding 100,000 degrees, blazing blue-white, pouring ultraviolet radiation into the surrounding darkness. The most massive of these population 3 stars shine with luminosities millions of times the Sun. Their radiation pressure is so intense it nearly blows them apart. They teeter on the edge of stability, pulsating, ejecting mass in violent eruptions. Their lifespans are measured in millions of years, perhaps only 1 or 2 million for the most massive, compared to 10 billion years for the Sun. These first stars are crucially important for cosmic evolution. They are the first objects to emit significant light, ending the cosmic dark ages. Their ultraviolet radiation begins ionizing the surrounding hydrogen, creating expanding bubbles of ionized gas. These ionized regions eventually overlap and merge, reionizing the universe. But their most important contribution comes when they die. These massive stars burn through their fuel rapidly, fusing hydrogen to helium, helium to carbon and oxygen, progressing through heavier elements all the way to iron. When fusion can proceed no further, when the star's core becomes iron, energy generation stops. Without pressure to support it, the core collapses catastrophically in less than a second. The collapse releases enormous energy. The outer layers of the star, still falling inward, encounter the rebounding core and are blasted outward in a supernova explosion. In this explosion, conditions become so extreme that elements heavier than iron are formed through rapid neutron capture. Gold, platinum, uranium, all the heavy elements are created in seconds during supernova explosions. These newly forged elements are ejected into space at thousands of kilometers per second, enriching the surrounding gas. For the first time, the universe contains significant amounts of carbon, oxygen, silicon, iron, and other elements. This enrichment changes everything. Gas with even trace amounts of heavy elements can cool much more efficiently. Carbon and oxygen atoms have many energy levels, allowing them to radiate across a broad range of wavelengths. Enriched gas can fragment into smaller clumps, forming smaller, longer-lived stars, more like those we see today. Some of the most massive population 3 stars may not explode at all. If massive enough, their cores collapse directly to form black holes. These black holes, containing tens or hundreds of solar masses, may serve as seeds for the supermassive black holes we find at galaxy centers today. Through accretion of surrounding gas and through mergers with other black holes, these seeds grow over billions of years, eventually reaching millions or billions of solar masses. The first galaxies begin to assemble around these early stellar populations. These are not the grand spiral or elliptical galaxies we see nearby. They are small, irregular, chaotic systems containing only millions of stars, perhaps tens of millions. They are the building blocks, the Lego pieces from which larger structures will be constructed through mergers and accretion over cosmic time. And they bring light back to the universe. The dark ages are ending. The cosmos is illuminated once more, this time not by the primordial fireball of the Big Bang, but by stars, localized nuclear furnaces scattered throughout space. The universe will never be truly dark again. As the first generations of stars flood the universe with ultraviolet radiation, something dramatic begins happening to the neutral hydrogen that fills space. Ultraviolet photons are energetic ionized to ionize hydrogen atoms, knocking electrons free from protons. Around each young galaxy, a bubble of ionized gas expands as starlight ionizes its surroundings. At first, these bubbles are small and isolated, tiny cleared regions surrounded by vast oceans of neutral gas. But as more galaxies form and more stars ignite, the bubbles grow and begin overlapping. Slowly, gradually, the neutral hydrogen is ionized. By roughly 1 billion years after the Big Bang, the process is largely complete. The universe has transitioned from neutral to ionized, from opaque to transparent at ultraviolet wavelengths. This is reionization, the epoch when the universe transforms from darkness to light, when stars win their battle against the neutral fog that fills space. It is a milestone, a phase transition in cosmic history. After reionization, the universe remains transparent to most wavelengths of light, the state it is in today. We can see across vast distances because the space between galaxies is ionized and transparent. But reionization is not just about transparency, it also affects structure formation. Ionized gas is hot gas, heated by the ultraviolet photons that ionize it. Hot gas has high pressure and resists gravitational collapse. In small dark matter halos, those containing less than perhaps a billion solar masses of material, the pressure from ionized gas can overcome gravity, preventing gas from cooling and forming stars. This heating may explain why small galaxies are less common than simple extrapolations from dark matter theory predict. The smallest halos exist, filled with dark matter, but contain no stars because the gas is too hot to collapse. In larger halos, gravity wins despite the heating. Gas continues flowing in, cooling, forming stars. These systems will become the galaxies we see today. Let us step back and view the universe on larger scales, not individual galaxies, but vast regions encompassing millions of light years. When we do this, patterns emerge. Galaxies are not distributed randomly, but show clear organization. Some regions are dense with galaxies, others are nearly empty. The distribution has structure. This structure originates from the same density fluctuations created during inflation, visible in the cosmic microwave background. But now, billions of years later, gravity has amplified these tiny fluctuations into dramatic variations. What began as barely perceptible ripples has become a vast cosmic architecture. The growth follows predictable mathematics. In regions slightly denser than average, gravity pulls in more matter. This increases the density further, strengthening gravity, pulling in even more matter. The process feeds on itself, exponentially amplifying small differences. Meanwhile, matter flows out of underdense regions toward overdense ones, evacuating voids and feeding filaments and clusters. But the growth is not uniform in all directions. The initial fluctuations from inflation have complex three-dimensional shapes. Some regions are elongated in one direction, compressed in others. As these structures collapse under gravity, they preserve and enhance these asymmetries. Consider an overdensity shaped like a cigar, long in one direction but narrow in the others. As it collapses, it shrinks fast as perpendicular to its long axis. The elongation becomes more pronounced. Material flows toward this structure preferentially along its length, creating a filament. Multiple such filaments can intersect, creating nodes where galaxy clusters form. Now imagine a pancake-shaped overdensity, thin in one direction, but extended in two others. This collapses primarily in its thin direction, becoming an even thinner sheet or wall. Galaxies form along this sheet, creating two-dimensional structures visible from certain viewing angles as concentrations of galaxies with little depth. The universe develops this web-like structure not through chance, but through the geometric properties of the initial density field and the anisotropic nature of gravitational collapse. The patterns we observe today were encoded in the primordial fluctuations, waiting to be revealed by billions of years of gravitational evolution. If we could somehow mark the dark matter and ordinary matter in the universe with glowing paint and step back to view the whole structure, we would see something extraordinary. A vast three-dimensional web of filaments and sheets, like a cosmic spider web or neural network, stretching across the observable universe. The densest knots in this web are galaxy clusters, enormous concentrations containing hundreds or thousands of galaxies, each galaxy containing billions of stars. Clusters are the most massive bound structures in the universe, containing typically 1 million billion solar masses, most of it dark matter, much of it hot gas between the galaxies, and only a small fraction in the visible stars. A typical rich galaxy cluster spans several million light-years across. At its center, galaxies are packed so densely that they move at hundreds or even thousands of kilometers per second, whipping through the cluster in chaotic orbits maintained by the collective gravitational pull of the entire system. The space between galaxies is not empty but filled with hot gas, heated to tens of millions of degrees by the gravitational energy released as the cluster formed. This hot gas, called the intracluster medium, emits X-rays detectable by space-based telescopes. When astronomers image clusters at X-ray wavelengths, they see diffuse glows extending far beyond the visible galaxies, revealing where most of the normal matter actually resides. Surprisingly, there is more mass in this hot gas than in all the stars of all the galaxies combined. The stars are merely tracers, bright markers of structure, while most ordinary matter hides between them. Connecting the clusters are filaments, elongated structures stretching for tens or hundreds of millions of light-years. Filaments contain galaxies strung out like beads on a wire. The galaxies in filaments are flowing along the structure, gradually accreting onto clusters at the filament ends. Filaments are the highways of the cosmic web, channels along which matter flows. If you could tag a galaxy in a filament and watch over billions of years, you would see it slowly drift toward the nearest cluster. The journey takes billions of years, but it is inexorable. Gravity pulls the galaxy along the filament toward the dense knot at the end. Eventually, it arrives and merges into the cluster, adding its mass to the growing concentration. The filaments themselves are not static pipes but dynamic flows. Gas streams along them continuously, channeling from the voids toward the clusters. This flow can be detected through observations. Gas flowing along filaments absorbs light from background quasars, creating absorption lines in quasar spectra. By studying these absorption systems, astronomers can map the distribution of gas along filaments even though it is too diffuse to emit detectable light on its own. Between the filaments lie walls or sheets, two-dimensional surfaces where galaxies congregate. Sheets are less dense than filaments, but still contain significantly more galaxies than average. They form the boundaries between empty regions. From certain angles, looking edge-on at a sheet, you see a concentration of galaxies forming a thin line across the sky. From other angles, looking face-on, you see galaxies spread across an area but with no depth, like a flat surface in three-dimensional space. These sheets are where many disk galaxies like the Milky Way reside. The environment is denser than the voids, but less violent than clusters. Galaxies in sheets and filaments experience fewer interactions and mergers than those in clusters, allowing them to maintain their disk structures and continue forming stars relatively undisturbed. And then there are the voids, vast empty spaces occupying most of the universe's volume. Voids are regions where galaxy density is very low, where almost nothing exists. They are not completely empty, but contain far fewer galaxies than average. Voids typically span 50 to 100 million light-years across, enormous cavities in the cosmic structure. Inside a void, you would see few, if any, galaxies. The nearest neighbor might be tens of millions of light-years away. The view would be profoundly different from our own, where galaxies are scattered throughout the sky. In a void, the sky would be mostly empty. galaxies visible only near the horizon in all directions, marking the walls surrounding the void. Void galaxies are unusual. They tend to be small, blue, star-forming systems. They have avoided the mergers and interactions common in denser environments, remaining isolated and relatively pristine. Some void galaxies may be fossils, ancient systems that have evolved slowly, undisturbed by external influences, preserving properties from earlier cosmic epochs. The universe is mostly empty space. If we could remove all the filaments, walls, and clusters, leaving only the voids, we would have removed only about 20 to 30% of the volume, but most of the matter. The voids contain comparatively little, their contents drained away over cosmic time as material flows toward denser regions. This web-like structure was predicted theoretically before being observed. Computer simulations starting from the tiny fluctuations seen in the cosmic microwave background and evolving forward using only gravity and the known components of the universe, dark matter, ordinary matter, and dark energy, naturally produce web-like structures remarkably similar to observations. This agreement is one of modern cosmology's great triumphs, strong evidence that we understand the basic processes shaping the universe. The prediction came from analyzing how density fluctuations collapse. In the 1970s and 80s, before computers were powerful enough to simulate the full complexity, theorists worked out the mathematics of gravitational collapse in different geometries. They showed that elongated overdensities naturally collapse into filaments, while sheet-like overdensities become walls, and compact overdensities become knots. When they applied this mathematics to realistic initial conditions from inflation, they predicted a cosmic web would form. When observations in the 1980s and 90s finally mapped large-scale structure through galaxy redshift surveys, the predictions were confirmed spectacularly. The universe does have a web-like structure. The filaments and walls and voids are real, not artifacts of observation or analysis, but genuine features of cosmic architecture. This confirmation was profound. It meant that the chain of reasoning, from quantum fluctuations during inflation through the density perturbations visible in the cosmic microwave background, through the growth of structure via gravitational collapse, to the observed cosmic web, this entire chain was consistent. Each link connected correctly, the story held together. We can trace causation across 13 billion years and billions of light-years of space. We can point to a fluctuation in the CMB and say, that seed grew into this filament. We can predict where structure should be and observe that it is there. This predictive power, this ability to connect cause and effect across cosmic scales, represents science at its most successful. Let us trace the history of a single filament, a structure stretching 100 million light-years across space, connecting two galaxy clusters. In the cosmic microwave background, this region shows a barely perceptible elongation, a slight tendency for overdensities to align along a particular axis. The variation is less than 1 part in 100,000, essentially invisible without sophisticated statistical analysis. But it is there, a seed planted by inflation. As dark matter responds to gravity, this slight elongation becomes enhanced. Material flows toward the overdense axis from perpendicular directions. The region becomes increasingly filamentary, increasingly elongated. By 1 billion years after the Big Bang, a clear filament structure exists in the dark matter distribution. It is still diffuse, still subtle, but present. Ordinary matter, now decoupled from radiation, follows the dark matter. gas flows into the filament along perpendicular directions, compressed as it falls into the elongated potential well. This compression heats the gas somewhat, but it can cool by radiation. The gas settles into the filament's potential, eventually forming a warm, elongated cloud stretching between the clusters at the filament's ends. Within this cloud, the densest regions form stars and galaxies. These galaxies are not distributed randomly along the filament, but preferentially in certain locations where the filament is thickest, where it intersects other structures, where the potential is deepest. The result is a string of galaxies along the filament axis, each galaxy separated from its neighbors by millions of light years, but clearly aligned, clearly part of a larger structure. The filament is not static. Gas continues flowing along it, streaming from the voids toward the clusters. Galaxies move along the filament, some falling toward the clusters, others perhaps ejected by interactions back out into the filament. The whole structure is dynamic, evolving, alive in a sense, constantly changing as matter responds to gravity and as the universe continues expanding. Over billions of years, the filament persists even as individual galaxies within it evolve and change. It is a stable structure, a fundamental element of cosmic architecture, as much a feature of the universe as a mountain range is a feature of a planetary surface. 2 billion years after the Big Bang, the universe is filling with galaxies. Most are small by modern standards, containing millions to billions of stars rather than the hundreds of billions typical of large galaxies today. These small galaxies are the building blocks of structure, but they do not remain isolated. Because galaxies form in clusters and filaments, many are close neighbors. Gravity pulls them together, orbits decay. Eventually, galaxies collide and merge. These mergers are a fundamental aspect of structure formation, the means by which small galaxies assemble into larger ones. When two galaxies of similar size collide, the merger is dramatic. The galaxies approach at hundreds of kilometers per second. Their dark matter halos interpenetrate, stars passing through the spaces between other stars like two swarms of bees flying through each other. Individual stellar collisions are almost impossibly rare. Stars are too small and too far apart, but the gravitational effects are profound. Meanwhile, the gas behaves differently than the stars. Unlike stars, which pass through each other without collision, gas clouds collide directly. When gas clouds from the two galaxies meet at hundreds of kilometers per second, the collision shocks the gas, heating it to millions of degrees. The shocked gas radiates energy and cools, compressing into dense regions. These dense regions are ideal sites for star formation. The result is a starburst, an episode of intense star formation far exceeding the normal rate in either galaxy. Within just a few million years, millions or billions of new stars form, consuming much of the available gas. The newly formed stars are hot and blue, blazing with ultraviolet light. The galaxies brighten dramatically during starbursts, temporarily becoming some of the most luminous objects in the universe. Tidal forces distort the galaxies. Long tails and bridges of stars are pulled out, creating spectacular shapes. Gas clouds collide. Unlike stars, gas does interact directly, compressing and shocking, triggering intense bursts of star formation. The merger is not a smooth blending, but a violent, chaotic event, reshaping both systems completely. After several orbits spanning hundreds of millions of years, the galaxies finally coalesce. Their dark matter halos merge into a single larger halo. their stellar populations mix thoroughly. The gas, much of it consumed in starbursts or heated and expelled by supernova feedback, settles into a new configuration. At the centers of each galaxy lies a supermassive black hole. As the galaxies merge, the black holes begin orbiting each other, gradually spiraling closer as dynamical friction, gravitational interactions with surrounding stars and dark matter drains energy from their orbit. This process is slow, taking perhaps tens of millions of years even after the galaxies have merged. As the black holes spiral together, their orbital velocity increases. When the separation shrinks to just a few times the Schwarzschild radius, they begin emitting gravitational waves strongly. These waves carry away energy, causing the orbit to decay even faster. In the final seconds, the black holes whip around each other at significant fractions of light speed, before finally merging in a spectacular event, releasing more energy in gravitational waves than all the stars in the observable universe emit in light over the Fripe. Same period. The gravitational wave signal from such a merger, if it occurred in a galaxy a few billion light-years away, would be detectable by future space-based observatories like LISA. The signal would chirp, rising in frequency and amplitude as the black holes spiral together, reaching a crescendo at the moment of merger before ringing down as the final merged black hole settles into equilibrium. From this signal, we could measure the black hole's masses, spins, and orbital parameters with precision, learning about their properties in ways impossible through electromagnetic observations alone. The final product is a single larger galaxy, typically with a different morphology than either progenitor. Spiral galaxies, with their orderly rotating disks, often become elliptical galaxies with chaotic random stellar orbits and no disk structure. The merger has scrambled the ordered motion, replacing it with random motion, transforming a thin disk into a thick ellipsoid. Not all mergers are equal. Minor mergers, where a small galaxy merges with a much larger one, proceed differently. The small galaxy is gradually torn apart by tidal forces, its stars scattered into streams that orbit through the larger galaxy. These streams eventually phase mix, becoming indistinguishable from the main galaxy's stellar halo. But in the meantime, they remain visible, ghostly structures marking past merger events. Our own Milky Way is currently undergoing minor mergers. The Sagittarius dwarf elliptical galaxy is being torn apart by tidal forces, its stars forming streams that wrap around the Milky Way multiple times. Observations reveal these streams evidence of ongoing galactic cannibalism. The Magellanic Clouds, our satellite galaxies visible from the southern hemisphere, will likely merge with the Milky Way in several billion years, adding their mass to our own. Over cosmic time, this hierarchical merger process builds ever larger galaxies. The largest galaxies we see today, giant ellipticals containing 1 trillion stars, have experienced many major mergers. They are assembled from dozens or hundreds of smaller galaxies over billions of years. Each merger adds mass and complexity. Each merger brings fuel that can trigger star formation and feed the central black hole. We can trace this history through observation. When astronomers study distant galaxies, they see them as they were billions of years ago. These distant galaxies are typically smaller and more irregular than nearby galaxies, consistent with the hierarchical merger picture. We are watching galaxies in the process of assembly, seeing the building blocks before they merge into the massive systems we observe nearby. Our own Milky Way is expected to merge with the Andromeda Galaxy in roughly 4 billion years. When it happens, the night sky will transform. Andromeda will grow from a faint smudge to a spectacular bright cloud dominating the heavens. Over hundreds of millions of years, the two galaxies will distort, collide, separate, and collide again before finally merging into a single elliptical galaxy. Any observers who survive the event, and the sun should continue shining so life on Earth is not directly threatened, will see a completely different sky. The familiar constellations will be scrambled as stars are redistributed by tidal forces. New regions of intense star formation will blaze across the sky. The merged galaxy's core, now containing two supermassive black holes spiraling together, may shine brilliantly as they feed on gas funneled inward by the merger. It will be a cosmic spectacle unlike anything visible today, a reminder of the dynamic, evolving nature of the universe. The Milky Way does not exist in isolation. We are part of a structure called the Local Group, a collection of over 50 galaxies dominated by the Milky Way and Andromeda. The Local Group occupies a region about 10 million light-years across. But the Local Group is itself part of something larger, the Virgo supercluster, a massive structure containing tens of thousands of galaxies, extends across 110 million light-years. At its heart lies the Virgo cluster, an enormous concentration of over 1,000 galaxies dominated by giant ellipticals formed through countless mergers. We sit on the outskirts of this supercluster, in a small spur or filament extending from the main concentration. The Virgo cluster's gravity pulls on us. Despite the universe's expansion, despite the stretching of space, the Virgo cluster is massive enough that its local gravity dominates. We are slowly falling toward it, though the infall is so gradual that the journey will take billions of years. Mapping the Virgo supercluster reveals structure within structure. Smaller groups and clusters form filaments and walls stretching across the supercluster. Voids lie between these structures. It is fractal-like, self-similar across scales, the cosmic web repeating its patterns on different size scales. But even the Virgo supercluster is not the largest structure. It is part of something bigger still. Recent surveys mapping galaxy motions across hundreds of millions of light-years have revealed an even larger structure, a supercluster of superclusters called Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea contains roughly 100,000 galaxies with a total mass of 100 million billion suns, spanning 520 million light-years. Laniakea is defined not by distance, but by flow. Galaxies within Laniakea are all flowing toward a common center of mass called the Great Attractor, an enormous concentration of mass in the direction of the Centaurus and Norma constellations. The Great Attractor itself may be part of an even larger concentration, the Shapley supercluster, one of the largest known structures in the universe. The boundaries of Laniakea are not walls or edges, but watersheds, analogous to drainage basins on Earth's surface. On one side of the watershed, galaxies flow toward the Great Attractor. On the other side, they flow toward other attractors, other centers of mass. The watershed marks where flows separate, where gravitational influence shifts from one supercluster to another. Understanding structures like Laniakea requires mapping not just where galaxies are, but how they move. Galaxies have two velocity components, one from cosmic expansion, the Hubble flows stretching space itself, and one from local gravitational influences, peculiar velocities caused by nearby mass concentrations. By measuring redshifts and accounting for expansion, astronomers can determine peculiar velocities, revealing how galaxies flow along the cosmic web. These flows trace the mass distribution, including dark matter. By mapping flows, we map the gravitational landscape, revealing where mass concentrates even when we cannot see it directly. The result is a three-dimensional map of structure, showing not just galaxies, but the rivers of matter flowing between them, the currents of the cosmic ocean. Are there structures even larger than Laniakea? Where does cosmic structure end? Observations reveal structures across a remarkable range of scales. Individual galaxies span hundreds of thousands of light years. Galaxy groups span millions. Clusters span tens of millions. Filaments extend hundreds of millions. Superclusters reach several hundred million. Beyond this, observations become ambiguous. Some astronomers have claimed detections of structures spanning billions of light years, enormous walls or supercluster complexes that seem to violate the cosmological principle, the assumption that the universe is homogeneous and isotropic on the largest scales. If confirmed, such structures would pose problems for cosmological models. But most evidence suggests the universe becomes effectively uniform beyond about 1 billion light-years. Local fluctuations, regions slightly denser or less dense than average, are common on scales of hundreds of millions of light-years. But average over several billion light-years and the universe looks remarkably similar in all directions. Galaxy counts, mass distributions, large-scale flows all become approximately uniform on these vast scales. This transition from structured to uniform, from inhomogeneous to homogeneous, typically occurs around 300 to 500 million light-years, sometimes called the homogeneity scale. Below this scale, structure dominates. Above it, the universe is essentially featureless, conforming to the cosmological principle that the universe has no special places, no center, no edge, appearing approximately the same from any vantage point. This observation is profound. It means the cosmic web, for all its complexity, is a local phenomenon in cosmological terms. The filaments, walls, clusters, and voids are fluctuations superimposed on an otherwise uniform universe. They are ripples on the cosmic ocean, significant in their own right, but not fundamentally changing the universe's large-scale properties. In the late 1990s, two teams of astronomers studying distant supernovae made a surprising discovery. Type Ia supernovae, thermonuclear explosions of white dwarf stars reaching consistent peak luminosities, serve as excellent standard candles for measuring cosmic distances. By observing supernovae in galaxies billions of light-years away, astronomers can determine how the universe's expansion rate has changed over cosmic time. The expectation was straightforward. The universe's expansion should be slowing down. Gravity attracts all matter, pulling galaxies together, opposing the expansion from the Big Bang. The expansion rate should decrease over time as gravity gradually wins, slowing the outward motion. The teams, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, observed dozens of distant supernovae, carefully measuring their brightness and redshifts. When they analyzed the data, they found something unexpected. The distant supernovae appeared fainter than predicted, dimmer than they should be if the universe's expansion were decelerating as expected. At first, the team suspected observational errors. Perhaps dust between us and the supernovae absorbed some light, making them appear dimmer. Perhaps the supernovae billions of years ago were intrinsically different from nearby ones, not perfect standard candles after all. The teams checked and rechecked, looking for mistakes, searching for alternative explanations. But the observations showed something else. Distant supernovae appeared fainter than expected, indicating they were farther away than predicted by models with decelerating expansion. The universe's expansion is not slowing down, it is speeding up. This discovery shocked the physics community. Accelerating expansion violated all expectations based on known physics. It required something completely new, something with bizarre properties unlike any known form of matter or energy. The teams published their results in 1998, and the findings were quickly confirmed by independent observations. The universe is dominated by something we do not understand, something with repulsive gravitational effects, something dubbed dark energy. This discovery, honored with the 2011 Nobel Prize in Physics, revealed that the universe is dominated by something we do not understand, something with repulsive gravitational effects, something dubbed dark energy. Dark energy differs fundamentally from both ordinary matter and dark matter. Matter, both ordinary and dark, gravitates attractively. More matter means stronger gravity, means slower expansion. But dark energy gravitates repulsively. More dark energy means faster expansion. And unlike matter, whose density decreases as the universe expands, dark energy appears to maintain constant density as space stretches. Every cubic meter of space contains the same dark energy, whether the universe is small or large. This constant density has profound implications. As the universe expands, the volume increases. If dark energy density remains constant while volume grows, the total amount of dark energy increases. Where does this energy come from? It appears to be created from nothing, from the expansion of space itself. This seems to violate energy conservation, one of physics' most fundamental principles. But the situation is more subtle. In general relativity, energy conservation is not a simple global law, but a local one. In expanding space, the concept of total energy becomes ambiguous. Dark energy's constant density can be consistent with general relativity if dark energy is a property of space itself rather than something within space. As space expands, more space means more dark energy, not energy flowing in from outside, but energy inherent to the fabric of space. Current measurements indicate dark energy comprises about 68% of the universe's total energy density. Dark matter accounts for about 27%. Ordinary matter, everything made of atoms, everything we can see and touch, amounts to only about 5%. We are a small minority in a universe dominated by mysterious, invisible components. The universe was not always dominated by dark energy. In the early universe, when everything was compressed into a smaller volume, matter density was much higher. Dark energy density remained constant, but matter density was enormous. Gravity from matter dominated, slowing expansion. As the universe expanded, matter density decreased, eventually becoming comparable to dark energy density. This transition occurred relatively recently in cosmic history, about 5 billion years ago. Since then, dark energy has dominated, driving accelerating expansion. Dark energy's existence changes the universe's future. Without dark energy, the universe might eventually stop expanding and recollapse in a big crunch, or continue expanding forever but at ever-slowing rates. With dark energy, the universe will expand forever at an accelerating rate. Galaxies beyond our local group will recede faster and faster until they disappear beyond the cosmic horizon, their light unable to reach us through the exponentially expanding space. This has sobering implications. Billions of years in the future, observers in the Milky Way will see only their local group surrounded by darkness, all evidence of the larger universe lost beyond the horizon. The cosmic microwave background will be redshifted to undetectably long wavelengths. Distant galaxies will have receded beyond visibility. Future astronomers will have access to far less information about the universe than we do today. They might conclude their local group is all that exists, unaware of the vast cosmos beyond their observational horizon. But there are more immediate implications for structure formation. Dark energy opposes structure growth. Gravity tries to pull matter together into denser structures. Dark energy tries to pull space apart, opposing collapse. As the universe ages and dark energy's influence grows relative to matter, structure formation slows and eventually stops. The cosmic web is nearly fully formed. The major filaments and clusters are in place. Future evolution will involve mergers and rearrangements of existing structures, but little new large-scale structure formation. In fact, structures that are not already gravitationally bound will never become bound. Galaxy groups and clusters held together by their own gravity will remain intact. But larger structures like superclusters, where galaxies are only loosely bound, will be disrupted by accelerating expansion. The cosmic web itself, on the largest scales, will gradually dissolve as space stretches faster than gravity can pull matter together. We do not know what dark energy is. Several possibilities exist, each with implications for fundamental physics. The simplest explanation is that dark energy is vacuum energy, the energy of empty space itself, predicted by quantum field theory. In quantum mechanics, vacuum is not truly empty, but filled with virtual particle pairs constantly appearing and disappearing, borrowing energy from the uncertainty principle for brief moments. These fluctuations contribute to vacuum energy density, giving empty space itself an energy content. The problem is the predicted vacuum energy density is wrong by a factor of 10 to the power of 120, the largest discrepancy between theory and observation in all of physics. Theory predicts an absurdly large vacuum energy that should have caused the universe to expand so fast that atoms could not form, let alone galaxies. Yet we observe a small but non-zero value, just large enough to cause accelerating expansion, but not so large as to prevent structure formation. This discrepancy is the cosmological constant problem, one of the deepest mysteries in theoretical physics. Why is the vacuum energy density so small? Is there some undiscovered symmetry or mechanism cancelling most of the predicted value? Or is our understanding of quantum field theory in curved spacetime fundamentally flawed? An alternative explanation is that dark energy is not constant but changes over time, a dynamical field called quintessence. Quintessence would be a new fundamental field, not previously encountered, with properties carefully tuned to produce the observed accelerating expansion. Different quintessence models make different predictions about how dark energy density changes over cosmic time. Other proposals invoke modifications to general relativity. Perhaps gravity operates differently on cosmological scales than on laboratory or solar system scales. Perhaps Einstein's equations require additional terms that become important at low densities or large distances. These modified gravity theories face challenges explaining all observations simultaneously, but remain active areas of research. The truth is, we do not know. Dark energy remains mysterious, a component dominating the universe's evolution yet completely unexplained by current fundamental physics. Resolving this mystery will likely require new observations and perhaps new physics beyond the standard model of particle physics and general relativity. Dark matter is equally mysterious. We know more about what it is not than what it is. It is not ordinary matter that happens to be dark. There is not enough ordinary matter in forms like black holes, brown dwarfs, or cold gas to account for the observed gravitational effects. Big Bang nucleosynthesis, the formation of light elements in the early universe, tightly constrains the total amount of ordinary matter. The observed abundances of hydrogen, helium, and lithium match predictions only if ordinary matter comprises about 5% of the universe's total energy density. Dark matter must be something else. It is not neutrinos. Neutrinos are fundamental particles that interact only through the weak nuclear force and gravity, making them difficult to detect. They exist in large numbers, perhaps hundreds per cubic centimeter, throughout the universe. But neutrinos are too light and move too fast to explain dark matter. Fast-moving particles, called hot dark matter, would smooth out structure on small scales, preventing galaxy formation. Observations require cold dark matter, slow-moving particles that can clump and form structures. Leading candidates are WIMPs, weakly interacting massive particles. These hypothetical particles would have masses perhaps 10 to 1,000 times the proton mass and interact through the weak nuclear force. If they exist, WIMPs would have been created in the early universe and survived to the present day. Their weak interactions mean they rarely collide with ordinary matter, making them difficult to detect, but allowing them to remain invisible while still exerting gravitational effects. Decades of experimental searches have not yet detected WIMPs directly. Deep underground laboratories, shielded from cosmic rays, operate detectors cooled to near absolute zero, waiting for the rare event when a WIMP collides with a detector nucleus. So far, no confirmed detections, though some controversial hints remain unexplained. Other candidates include axions, extremely light particles proposed to solve problems in quantum chromodynamics. Actions would be produced copiously in the early universe and could constitute dark matter despite their tiny individual masses. Sterile neutrinos, hypothetical partners to known neutrinos, are another possibility. Primordial black holes formed in the early universe represent yet another candidate, though observations constrain how much dark matter can be in this form. Or perhaps dark matter is something completely unexpected, a particle or phenomenon not yet imagined by theorists. The universe has surprised us before. Dark energy was unexpected. The acceleration of expansion was a shock. Perhaps dark matter will prove equally surprising when finally understood. Whatever dark matter is, it shaped the universe. Without dark matter, structure formation would have proceeded too slowly. galaxies would be rare or non-existent. The cosmic web would not have formed. Life as we know it depends on structures like galaxies and stars, structures that could not exist without dark matter's gravitational influence. We owe our existence to something we do not understand. Understanding how the universe developed its structure requires more than observation and theory. It requires computation. The equations governing structure formation, the growth of density fluctuations under gravity, the flow of gas, the formation of galaxies, are far too complex to solve analytically. Computer simulations provide the only way forward. Modern cosmological simulations start with initial conditions representing the universe shortly after the Big Bang. These conditions include the density fluctuations created during inflation and observed in the cosmic microwave background. The simulation volume might span hundreds of millions or even billions of light-years, containing billions of particles representing both dark matter and gas. The simulation then evolves forward in time. Each particle feels gravitational forces from all other particles. In principle, this requires calculating forces between every pair of particles, a computational task scaling as the number of particles squared. For billions of particles, direct calculation would be impossibly slow. Instead, simulations use clever algorithms, grouping distant particles and calculating collective forces, reducing computational cost dramatically. One common approach is the tree algorithm. The simulation volume is divided into cubic cells. Cells are recursively subdivided into smaller cells, creating a hierarchical tree structure. When calculating forces on a particle, distant groups of particles can be treated as single massive objects if they are sufficiently far away and clustered closely together. This reduces the number of force calculations from billions squared to something closer to billions times the logarithm of billions, a tremendous savings. Another approach uses particle mesh methods, where particles contribute to a density field defined on a regular grid. Forces are calculated from this grid using fast Fourier transforms. This method is very efficient for long-range forces, but struggles with closely spaced particles where resolution matters. Hybrid methods combining trees and meshes capture both long-range forces efficiently and short-range forces accurately. As the simulation proceeds, structure emerges naturally from the initial conditions. Overdense regions attract more matter and grow denser. Underdense regions lose matter and become voids. The cosmic web takes shape, filaments and walls and clusters appearing without being explicitly programmed. They are emergent phenomena arising inevitably from gravity acting on the initial density field. But gravity alone is not enough to reproduce observations. We must also simulate gas physics, the behavior of ordinary matter beyond simple gravitational attraction. Gas has pressure that resists compression. It can heat and cool through radiation. It can form stars, which then explode as supernovae, injecting energy back into the gas. Supermassive black holes can grow and power quasars, heating surrounding gas and driving winds. Adding all these processes requires sophisticated subgrid models, prescriptions for what happens at scales smaller than the simulation can resolve. Individual stars cannot be simulated in a cosmological volume. Each would require its own particle, impossibly expensive computationally. Instead, star formation is modeled statistically. When gas reaches sufficient density and temperature, a fraction converts to stars according to empirically calibrated rules. Similarly, supernova feedback must be modeled. When stars form, some fraction will explode as supernovae. These explosions inject energy into surrounding gas. The simulation must decide how much energy, where it goes, how it couples to gas. Different choices produce different results. Fine-tuning these subgrid models to match observations is an ongoing challenge. The largest simulations run on supercomputers using thousands or tens of thousands of processor cores working in parallel. A single simulation might run for weeks or months, consuming millions of CPU hours. The data produced can reach hundreds of terabytes, requiring specialized facilities for storage and analysis. Running a cosmological simulation is like conducting an experiment, but the experiment happens inside a computer rather than a laboratory. We set initial conditions, specify physical laws, and let the simulation evolve. The outcome tells us what our theories predict. By comparing simulated universes to observations, we test whether our understanding is correct. One landmark simulation, the Millennium simulation completed in 2005, followed the evolution of over 10 billion particles in a cube 2.5 billion light-years on a side. The simulation began when the universe was 1 million years old and evolved forward to the present day, tracking 13 billion years of cosmic history. The computational challenge was immense. 10 billion particles, each interacting gravitationally with all others, evolved through many millions of time steps. The simulation ran on a supercomputer at the Max Planck Institute for Astrophysics in Germany, using over 500 processors running continuously for more than a month. The output data exceeded 25 terabytes. The Millennium simulation revealed the cosmic web in exquisite detail. Filaments stretched across the simulation volume, connecting dense knots where massive galaxy clusters form. Voids opened up as matter drained from underdense regions. Statistical properties of the simulated universe matched observations remarkably well, providing confidence that the underlying physical model is correct. One powerful feature was the ability to trace structures back in time. Researchers could identify a massive galaxy cluster in the final output and follow its history backward, watching it form through mergers of smaller clusters, which themselves formed from groups, which formed from individual galaxies, tracing the entire merger tree back to the earliest seeds. This hierarchical assembly, impossible to observe directly since we see each object at only one moment in time, became clear in the simulation. Subsequent simulations have pushed further. The Millennium 2 simulation used over 10 billion particles in a smaller volume to achieve higher resolution, resolving structures down to individual galaxy scales. This allowed detailed study of galaxy formation and evolution, processes operating on scales much smaller than the cosmic web, but connected to it. The illustrious simulation, completed in 2014, represented another major advance. It used 12 billion particles and included not just dark matter, but gas physics, star formation, supernova feedback, and black hole growth, attempting to simulate a complete universe, including baryonic processes. The volume was smaller than Millennium, about 100 million light-years on a side, but the added physics made the simulation far more complex and computationally expensive. The illustrious simulation produced realistic galaxies with properties matching observations. Spiral galaxies formed with rotating disks. Elliptical galaxies formed through mergers. Galaxy colors, sizes, star formation rates, and other properties aligned with observed values. When simulated telescopes photographed the simulated universe, the results looked remarkably like real telescope images. This was powerful validation. Not only did the simulation reproduce the cosmic web, it reproduced individual galaxies within that web. But challenges remained. Some galaxy properties did not match perfectly. The most massive galaxies sometimes formed too many stars. Small galaxies sometimes had different dark matter distributions than observed. The discrepancies highlighted gaps in understanding, particularly of feedback processes regulating galaxy formation. The TNG simulations, Illustris TNG, represent the current state of the art. These simulations improve the feedback models based on lessons from Illustris. Multiple volumes at different resolutions allow studying phenomena from individual galaxy properties to large-scale structure. The largest TNG simulation follows over 30 billion particles in a cube 1 billion light-years across, while smaller volumes with higher resolution zoom in on individual galaxies. These simulations match observations across an impressive range of properties, from the cosmic web on the largest scales down to galaxy structure on small scales. They reproduce the galaxy luminosity function, describing how many galaxies of each brightness exist. They match observed galaxy sizes, colors, morphologies, and star formation rates. They show realistic quasar populations and supermassive black hole growth histories. Yet challenges remain. Some properties still do not match observations perfectly. The most massive galaxies in simulations sometimes form too many stars. Small galaxies sometimes have too much dark matter concentrated at their centers. Fine-tuning feedback processes, adjusting how supernova energy couples to gas or how black holes affect their surroundings, can improve agreement but raises questions about whether we truly understand the physics or are just adjusting parameters to match observations. This tension between detailed modeling and empirical calibration is inherent to the field. We cannot simulate every physical process from first principles. Some processes, like star formation within molecular clouds or supernova explosions, operate on scales far too small to resolve in cosmological simulations. We must use approximate models calibrated against observations and smaller scale simulations. The question is whether these models capture the essential physics or whether we are missing important processes. Despite these challenges, simulations have become indispensable tools. They allow testing theories in ways impossible through observation alone. They reveal how structure forms, how galaxies evolve, how the cosmic web emerges. They connect the distant past, visible in the CMB, to the present-day structure we observe. They predict what future observations should see, guiding telescope design and observing strategies. They are our window on cosmic history, letting us watch the universe evolve in ways we can never directly observe. Simulations provide insights impossible to gain from observations alone. We can watch structure formation happen, something observationally impossible since we see each object at only a single moment in time. We can zoom in on any structure and trace its history backward, identifying which smaller structures merged to form it, following the merger tree back to the earliest seeds. Simulations reveal the importance of mergers. Nearly every massive galaxy has experienced multiple major mergers. Mergers trigger star formation, reshape morphologies, feed black holes, and build up stellar populations. The random violence of mergers is fundamental to structure formation, not a rare anomaly, but a central process. Simulations also show how feedback regulates galaxy formation. Without supernova feedback, simulations produce galaxies with too many stars and too little gas. Without black hole feedback, the most massive galaxies grow too large. Feedback is essential for matching observations, providing evidence that these processes are important in the real universe. Simulations demonstrate the role of environment. Galaxies in dense environments like clusters evolve differently than those in voids. Cluster galaxies experience ram pressure stripping when moving through hot intra-cluster gas, losing their own gas and quenching star formation. Void galaxies remain isolated and gas-rich, continuing to form stars long after cluster galaxies have stopped. These environmental effects, predicted by theory and confirmed by simulations, are observed in real galaxy populations. Perhaps most importantly, simulations test our fundamental model of structure formation. The fact that simulations starting from observed initial conditions and evolving forward using only known physics produce universes remarkably similar to our own is powerful evidence that we understand structure formation's basic principles. Details remain uncertain, but the overall picture appears correct. Dark matter is invisible. It does not emit, absorb, or scatter light. How do we map something we cannot see? The answer is gravitational lensing. Mass warps spacetime. Light traveling through warped spacetime follows curved paths. When light from distant galaxies passes near massive structures like galaxy clusters, the light is bent, distorted, magnified. The background galaxies appear stretched and distorted, their images smeared into arcs or even complete rings around the foreground cluster. By analyzing these distortions, measuring how background galaxy shapes are changed, astronomers can infer the distribution of mass in the foreground cluster. This technique, called weak gravitational lensing, works even when individual distortions are subtle. By averaging over many background galaxies, the overall mass distribution emerges. Remarkably, mass maps created through gravitational lensing do not match the distribution of visible galaxies. Most of the mass is not where the light is. Instead, mass traces an extended halo surrounding and between the visible galaxies, the distribution expected for dark matter. These observations provide direct evidence for dark matter's existence and map its distribution independent of any assumptions about galaxy light. The most dramatic demonstration comes from the Bullet Cluster, two galaxy clusters that have passed through each other in a high-speed collision. The galaxies, which are mostly empty space, pass through largely unaffected. The hot gas between galaxies, which interacts electromagnetically, collides and is shocked, remaining near the collision site and emitting X-rays. But gravitational lensing reveals that most of the mass, the dark matter, has continued moving with the galaxies, now well separated from the hot gas. This observation is difficult to explain without dark matter. If we tried to explain gravitational effects by modifying gravity instead of invoking dark matter, we would expect the gravitational center to coincide with the gas where most visible mass resides. Instead, the gravitational center coincides with the galaxies. Dark matter provides a natural explanation. The dark matter halos around each cluster pass through each other unaffected, just like the galaxies, because dark matter interacts only gravitationally. Understanding large-scale structure requires three-dimensional maps. Photographs show galaxies on the sky, but not their distances. To map structure, we need distance information for millions of galaxies. This is where redshift surveys come in. By measuring the redshift of each galaxy's spectrum, astronomers determine its distance using the Hubble relation between redshift and distance. Combining position on the sky with distance gives a three-dimensional coordinate for each galaxy. With enough galaxies, the cosmic web emerges. Early surveys like the CFA Redshift Survey in the 1970s and 80s mapped thousands of galaxies, revealing for the first time that galaxies cluster and form filamentary structures. The universe was clearly not uniform on scales of tens of millions of light-years. The 2-degree Field Galaxy Redshift Survey, completed in 2003, mapped over 220,000 galaxies, creating the first comprehensive three-dimensional map of large-scale structure. The Sloan Digital Sky Survey, an ongoing project since 2000, has measured redshifts for millions of galaxies across much of the sky. These surveys reveal the cosmic web in stunning detail. We see filaments connecting clusters. We see walls of galaxies surrounding voids. We see hierarchical structure, smaller structures nested within larger ones. Statistical analysis reveals the characteristic scales of structure, typically hundreds of millions of light-years, matching theoretical predictions. Future surveys will push deeper and wider. The Dark Energy Spectroscopic Instrument, DESI, aims to measure 35 million galaxy redshifts over 5 years. The Vera C. Rubin Observatory will create the deepest, widest survey ever, imaging billions of galaxies. The Euclid Space Telescope and Nancy Grace Roman Space Telescope will map structure to unprecedented distances and precision. These observations will refine our understanding of structure formation, measure dark energy's properties with increased accuracy, and test models of cosmology and gravity with ever greater rigor. The cosmic microwave background remains our best window on the early universe. Missions like COBE in the early 1990s, WMAP in the 2000s, and Planck in the 2010s have mapped the CMB with increasing precision, revealing the temperature variations across the sky in exquisite detail. These maps show the universe as it was 380,000 years after the Big Bang, before stars, before galaxies, just the primordial plasma beginning to form atoms. The tiny fluctuations, variations of only a few parts in 100,000, are clearly visible. These are the seeds that grew into all cosmic structure. By analyzing the CMB's statistical properties, particularly the angular power spectrum describing fluctuations at different scales, cosmologists extract fundamental parameters describing the universe. The total density, the matter density, the dark energy density, the Hubble constant, the age of the universe, all can be measured from the CMB with remarkable precision. The CMB also encodes information about inflation. The fluctuations' properties, their scale dependence, and statistical character match predictions from inflationary models. The CMB is slightly polarized, light waves preferentially aligned in certain directions, and this polarization contains information about gravitational waves produced during inflation. Detecting this signature remains a major goal of observational cosmology. Future CMB experiments will search for these signatures with increased sensitivity. ground-based telescopes in Chile and Antarctica observe the CMB at high angular resolution. Proposed space missions would map the entire sky with unprecedented accuracy. Each improvement constrains models more tightly, testing our understanding of the universe's first moments. We have traced structure formation from inflation through the cosmic dark ages through galaxy formation to the present day. But the story does not end here. The universe continues evolving. What does the future hold? Structure formation is nearly complete. The major filaments and clusters are established. Dark energy's accelerating expansion means that density contrasts will not grow much larger. The cosmic web has reached its mature state. But within this web, evolution continues. Galaxies continue merging. The Milky Way and Andromeda will collide in about 4 billion years. Other local group galaxies will eventually merge into the combined remnant. Over tens of billions of years, the local group will likely coalesce into a single giant elliptical galaxy containing all the mass of its progenitors. This future elliptical will be a quiet place compared to our current Milky Way. The merger will consume most of the available gas in starbursts, forming billions of new stars but exhausting the fuel supply. Once the merger completes and the starburst ends, little gas will remain. Star formation will decline to nearly zero. The galaxy will fade gradually as its stars age. Beyond the local group, other galaxies and clusters will recede ever faster as dark energy drives accelerating expansion. Eventually, they will cross the cosmic horizon, receding faster than light, not because they move through space at such speeds, but because space itself expands between us at such rates. Their light will never reach us again. The observable universe will shrink, containing fewer and fewer galaxies as time passes. This isolation is profound. Within perhaps 100 billion years, all galaxies beyond our local group will have crossed the horizon. An astronomer in the distant future, looking out at the universe, will see only the merged local group galaxy surrounded by darkness. The cosmic microwave background will have redshifted to such long wavelengths it becomes undetectable. There will be no evidence of other galaxies, no evidence of cosmic expansion, no evidence of the Big Bang. The universe will appear static and eternal, containing only a single galaxy in an unchanging void. This future astronomer, if they exist, will not be able to discover what we have discovered. They will lack the observational evidence we possess today. The expansion of the universe, dark energy, the cosmic web, all these discoveries depend on observing distant galaxies and the cosmic microwave background. Without access to these observations, future cosmology will be impossible. We are privileged to live in an epoch where the universe reveals its secrets. Star formation will continue for a while but gradually decline. Gas supplies are finite. Feedback from stars and black holes ejects or heats gas, preventing further star formation. In perhaps 1 trillion years, star formation will essentially cease. The galaxies will fade as their stars age and die. Low-mass red dwarf stars can shine for trillions of years, far longer than the current age of the universe. These will be the last stars, dim red embers slowly cooling over incomprehensible time spans. Red dwarfs burn their fuel so slowly, so efficiently, that they can continue for 100 trillion years or more. They convert almost all their hydrogen to helium before finally exhausting their fuel. When they finally die, they simply fade, becoming dim white dwarfs stellar corpses slowly radiating away their residual heat. When the last red dwarf finally dims, around 100 trillion years from now, the universe will become truly dark, containing only stellar remnants, white dwarfs, neutron stars, and black holes. No stars shine, no fusion occurs. The stelliferous era, the age of stars, has ended. But even this is not the end. On timescales of 10 to the 30 years or more, even these remnants may not be permanent. Protons might decay, a predicted consequence of some grand unified theories, though such decay has never been observed. If protons do decay, white dwarfs and neutron stars would gradually evaporate, their constituent particles decaying into lighter particles and energy. The theoretical predictions suggest protons have lifetimes of at least 10 to the 34 years, possibly much longer. This is so long that we cannot hope to observe individual proton decays directly. The best experiments involve watching enormous numbers of protons, hoping to catch one decay. So far, no confirmed detections exist, pushing the lifetime limit higher with each passing year. If protons do decay, the implications are profound. All atomic nuclei would eventually disintegrate. White dwarfs, made of carbon and oxygen nuclei, would evaporate into radiation. Neutron stars made of tightly packed neutrons would similarly decay. Even planets and interstellar dust would fade away. Only black holes would remain, immune to proton decay, because their matter has already collapsed beyond the event horizon. Black holes will evaporate through Hawking radiation, but unimaginably slowly. A solar mass black hole requires 10 to the 67 years to evaporate. A supermassive black hole requires 10 to the 100 years. These timescales are so vast that the universe's current age is negligible by comparison. Writing out 10 to the 100th power in full requires a 1 followed by 100 zeros. Current estimates put the universe's age at about 10 to the 10th power years. The ratio between these timescales is incomprehensible. Yet even black holes must eventually evaporate. Hawking radiation, the quantum process by which black holes emit particles and lose mass, proceeds inexorably. Slowly, almost imperceptibly, black holes shrink. As they shrink, their temperature rises. Smaller black holes evaporate faster than large ones. The final moments of black hole evaporation are spectacular, a tiny quantum black hole radiating enormous power before vanishing in a burst of particles and energy. The far future universe will be cold, dark, and empty. Maximum entropy, thermal equilibrium, the heat death. Nothing happens because nothing can happen. All useful energy has been expended. All structure has decayed. Only isolated black holes remain, slowly evaporating into the void. And when the last black hole evaporates, the universe will contain only dilute radiation, photons and particles spread across space, gradually cooling as space continues expanding, approaching but never quite reaching absolute zero. This far future seems bleak, devoid of interest or complexity. But we should remember that it is unimaginably distant. More time will pass between now and then than has passed since the Big Bang, not by a little, but by factors of trillions upon trillions. The entire history we have traced, from inflation to the present day, is a tiny fraction of cosmic time. We live near the beginning, not the end. But we are not there yet. We live in what might be called the universe's golden age, the stelliferous era when stars shine and structure exists. We should appreciate our privileged position in cosmic time and use it to understand as much as we can. The universe is revealing its secrets to us now. Future civilizations, if they exist, may not have the same opportunity. Despite remarkable progress, fundamental questions remain unanswered. What is dark matter? Decades of theoretical work and experimental searches have not yet revealed its identity. Future experiments, more sensitive detectors, new search strategies may finally detect dark matter particles directly and reveal their properties. What is dark energy? Is it truly constant, or does it evolve with time? Is it vacuum energy or something more exotic? Observations over the next decades will measure dark energy's properties more precisely, distinguishing between models. What caused inflation? What is the inflaton field? Did inflation happen as theorists believe, or is some other mechanism responsible for the universe's properties? Observations of gravitational waves from inflation, if successful, would provide direct evidence for inflation and constrain models significantly. How exactly do galaxies form? Simulations reproduce many observed properties, but some discrepancies remain. Understanding feedback processes, how stars and black holes affect their surroundings, remains challenging. Observations of high redshift galaxies with the James Webb Space Telescope are revealing how galaxies looked shortly after formation, providing new tests of models. Are their structures even larger than superclusters? Where exactly does structure end and homogeneity begin? Observations continue pushing to larger scales, mapping structure across ever greater volumes. Is the universe truly homogeneous on the largest scales, or are there large-scale variations that would challenge the cosmological principle? Careful analysis of galaxy surveys and CMB observations continues testing this fundamental assumption. These questions will drive research for decades. Each answer will raise new questions. Science never finishes, but continually pushes back the boundary between known and unknown. We began by asking how the universe got its shape. The answer is a story spanning 13.8 billion years, from quantum fluctuations during inflation to the vast cosmic web we observe today. The universe got its shape through the interplay of several fundamental processes. Inflation stretched quantum fluctuations to cosmic scales, planting the seeds. Dark matter collapsed under gravity, building the invisible scaffolding. Ordinary matter followed, cooling and condensing, forming stars and galaxies. Feedback from stars and black holes regulated growth, preventing runaway collapse. Mergers assembled larger structures from smaller ones. And through it all, cosmic expansion stretched space, shaping the evolution of structure. The cosmic web, the filaments and walls and clusters separated by vast voids, is not random chaos, but organized structure following patterns determined by initial conditions and physical laws. It is predictable, understandable, even beautiful in its complexity. Yet this understanding highlights how much we do not know. The universe is dominated by dark matter and dark energy, components we cannot directly detect and do not fundamentally understand. The earliest moments, the era of inflation, remain speculative, supported by indirect evidence but not definitively proven. The ultimate fate of structure, the long-term evolution over timescales dwarfing the current age of the universe, remains uncertain. But this uncertainty does not diminish what we have achieved. In a few centuries, Humans have progressed from thinking Earth is the center of creation to understanding that we inhabit one planet orbiting one star among hundreds of billions in one galaxy, among hundreds of billions in an observable universe that may be an ETETL, one star among hundreds of billions, galaxy. Infinitesimal fraction of the entire cosmos. We have traced cosmic history from the first fraction of a second after creation to the present day. We have measured the universe's composition, its age, its expansion rate, its structure. This knowledge was hard-won through patient observation, creative theorizing, and rigorous testing. It required developing new technologies, new mathematics, new physical theories. It required collaboration across generations and across the globe. It remains incomplete, always incomplete, but remarkably successful within its domain. The universe has a shape. That shape emerged from simple beginnings through comprehensible processes. We can trace the path from nearly uniform simplicity to structured complexity. We can predict the future, at least in broad strokes. We can test our understanding through observation and simulation. This is the power of science. Not to answer every question, but to replace mystery with understanding, to find patterns in apparent chaos, to reveal that the universe follows rules we can discover and describe. The cosmic web stretches across billions of light years, yet we can hold its properties in our minds, capture them in equations, reproduce them in computer simulations. As we look out at the night sky, at the galaxies scattered across space, we now see not just lights in the darkness, but an organized structure. We see filaments connecting clusters. We see voids emptied of matter. We see the cosmic web in all its intricate beauty. And we understand, at least in part, how it came to be. The universe does not explain itself. We must figure it out through observation, reason, and imagination. The fact that this is possible, that minds evolved on one small planet can comprehend cosmic structure, is perhaps the deepest mystery of all. But it is also cause for wonder and humility. We are part of this cosmos, made of the same atoms forged in stellar cores, shaped by the same forces that shaped galaxies. Understanding cosmic structure is, in a sense, the universe understanding itself through us. The cosmic web is not just out there in space. It is part of the larger story of matter and energy, of structure emerging from simplicity, of complexity arising from basic laws. It is our story too. We are here because stars formed in galaxies that formed in the cosmic web that emerged from quantum fluctuations during inflation. Every step in that chain was necessary. Break any link, and we would not exist to ask these questions. There is something profound in realizing that we can trace our origins back to the universe's first moments. The atoms in our bodies were forged in stars that formed in galaxies that arose from density fluctuations created during inflation. We are, quite literally, stardust organized into patterns capable of contemplating our own origins. This is how the universe got its shape. Through inflation, through dark matter, through gravity and gas cooling, and star formation and feedback, and mergers, through billions of years of cosmic evolution. It is a story of structure emerging from simplicity, of order arising from near uniformity, of the universe slowly awakening to complexity. And we, improbable creatures on an unremarkable planet, orbiting an ordinary star in a typical galaxy, can understand it. That understanding is itself part of the universe's shape, part of how matter and energy have organized themselves in this corner of space and time. The journey from the Big Bang to the cosmic web is complete. Structure has emerged. The universe has found its shape, and we are here to witness it, to study it, to marvel at it. That, perhaps, is the most remarkable thing of all.